Okay, everyone, so here's a brief review about what you need to know about the atom and early developments in atomic theory. It all started for us with Dalton's proposals about the atom around 1808. And the big things to understand that he stated in his theory were as follows. He said all matter is composed of very small things called atoms. And this is in part due to the original hypothesis from Democritus, who was a Greek philosopher hundreds of years earlier, who stated that you got to a point where you could only minimize matter to a limit, and that limit he called atomos, an indivisible particle. And that's what Dalton is claiming here, that all matter is composed of small things called atoms. And Dalton also thought that every single atom of a given element was exactly the same. He said atoms couldn't be broken down into anything simpler, and that when atoms react with one another in chemical processes, that they combine in different ratios depending on what the elements are. And when you're having a reaction, there is some combining, separating, or rearrangement of atoms going on. So let's take a look at this now in light of what we know today. So look at this first premise, that atoms of a given element are exactly the same. This should strike you as wrong, because we know that there are things called isotopes, atoms of the same element that differ in their mass because they have different numbers of neutrons. So it's important to understand that in Dalton's theory, some of his premises have remained, but there also have been several changes made. Because we now know that atoms of an element have a characteristic average mass, which is due in part to the unique number of isotopes of that particular element. Let's look at a second piece. So Dalton also said that atoms cannot be subdivided, created, or destroyed. Now, we can actually subdivide, destroy, and transmutate atoms through nuclear processes, though. So the important thing to understand here is we can't create, destroy, or subdivide atoms in ordinary chemical reactions. So for us, that means in the chem lab, you're never going to create, subdivide, or destroy atoms. However, if you worked in a nuclear facility, these types of transmutation processes happen all the time, but only in nuclear reactions. So let's start to look at how our idea of the atom has changed. So Dalton's view is very much just this singular, indivisible particle. The work of Thomson changed that because Thomson discovered that there were negatively charged particles. And he noticed this through an experiment called a cathode ray tube experiment. The resulting change from that is that we now knew that there were some negative particles that existed. And Thomson also hypothesized that overall those atoms are neutral, so there must be also some positive charge as well. And there are equivalent amounts of positive and negative charge because overall atoms don't respond to anything in an electric field. So the model changes like this. Now where we just had an indivisible particle, notice that we have negative electrons and a positive diffuse area in our atom. And this is called the plum pudding model. Key thing to remember is the plum pudding model just shows the existence of negative electrons. Notice the proton is still not there. We just treat the rest of the atom as a diffuse kind of positive region of charge. Some things to take away from work involving the electron is that the way that we can claim that we know that electrons are all the same is because every cathode ray behaved exactly the same. If you put a positive end of a magnet near the stream of particles, the stream would bend up towards the magnet. That shows us that the charged particles had to be negative. And every element that Thomson did this experiment with behaved the same way. So the conclusion can be that all elements contain identically charged electrons. And the rest of this I think I've gone through. So let's skip on to Rutherford's gold foil experiment. Now Rutherford's initial premise was to validate Thomson's model. And he proposed to do this by taking a particle emitter, you see it here in this black box, that shot alpha particles. And alpha particles are really just helium nuclei. So they're pretty dense and heavy particles being shot at a very, very thin gold foil. And in class we talked about the thinness of this foil being only a few atoms thick. You can imagine if you held that foil up to the light, you could see through it. It would be transparent. And he hypothesized that if Thomson's model was correct, you would see every single alpha particle just go straight through it, kind of like a gun being shot at a piece of tissue paper. You wouldn't expect the bullets from the gun to deflect much at all. What he found instead was something quite extraordinary. He noticed that if you look at the diagram on the right, most of the particles went through with very little deflection. But there were occasions where an electron would bounce all the way back, not an electron, the alpha particle would bounce all the way back. And that was surprising because Thomson's model wasn't a model that showed any kind of extreme density. And what this shows, if you have a particle bouncing back like this, is that you have a region that's, first of all, very dense and positive in charge as well. And Thomson's work had not shown any of this. So through the result of Rutherford's gold foil experiment, we concluded the following. Most of the particles passed right through, we mentioned that. A few were greatly deflected, and very few bounced backwards. This was such a surprising result for him that he claimed it was like howitzer shells bouncing off of tissue paper. The conclusions that we draw from this is that there has to be something called a nucleus. There is a region of dense positive charge. And this is where our model changes to now have a model with a nucleus, which contains protons. And we also know it contains neutrons, although Rutherford's work didn't show this. And the electrons are relegated to orbitals orbiting around the nucleus. This is essentially what you need to know about atomic theory. Let's also briefly spend some time going over some extensions that come as a result of these findings. First, we should know some characteristics of atomic particles and where those particles are located as a result of Rutherford's model. Later on, we'll be studying additional atomic theory, but for right now, a Rutherford model is sufficient. First thing to know is electrons, which have a charge of -1, are located in an electron cloud. You could also call it an orbital or a shell. Protons and neutrons, those are found in the nucleus. And notice the difference in mass here. Protons and neutrons are about 1,000 times more massive than electrons are. That means we don't really take into account the mass of an electron when we're calculating the mass of a particular isotope of an element. And our model that we should be able to construct can look something like this. An example here is helium-4. Notice in the nucleus we see 2 positive protons, 2 neutrons, both of which contribute a mass of 1 atomic mass unit. Notice that's why we give it the designation helium-4. This diffuse gray cloud here is representative of the region of space where helium's 2 electrons might be orbiting. Something that I mentioned earlier is the existence of isotopes. It's a key thing that helped us to modify a portion of Dalton's atomic theory. And you've done some work on this previously, but just refresh your memory. Remember that if we're going to look at differences in isotopes, and here you see 3 different isotopes of hydrogen, the core difference is not in anywhere but the nucleus. So if we look at the nucleus of a hydrogen 1 atom, protium, all we see is a single proton. For hydrogen 2, we would see 2 particles, 1 proton, 1 neutron. And for hydrogen 3, we would see, again, 1 proton and 2 neutrons. So notice the thing that's the same, the thing that defines the element. It's the number of protons in the nucleus and nothing else. So when we find an average, which now we're getting into in class in our second unit of study, we start to consider the average of all the natural types of isotopes of a particular element that exist in nature. You can see here in the table that I'm showing you some examples of carbon, much like the examples we've talked about when I initially introduced this in class. So notice that most of the carbon atoms that exist are of a particular type, carbon-12. Fewer are carbon-13, and even fewer are carbon-14. When we take the average, we don't just simply add the masses together and then divide by 3. We have to do a weighted average. And you've practiced this in the past, so I'd encourage you to go back and look at your notes and the examples that you've done previously for determining how to calculate a weighted average. But when we calculate a weighted average for something like carbon, we would expect the average to be much closer to 12 because most of the atoms of carbon happen to be carbon-12 isotopes. Some other things to remember is just how we can use characteristics that we find on the periodic table to determine subatomic features about different elements. Remember that the atomic number, which is on our periodic table, is the number that's listed on top of the elemental symbol on the periodic table. that is equal to the number of protons. That's the thing that defines the elements. And the atomic number also tells us the positive charge of the nucleus. Now we can use this, in addition with the mass number, to figure out all of the defining characteristics of a particular isotope. So pause the video right now and see if you can recall how to do this. Try and fill in the values in the table. Remember that the mass number tells you protons and neutrons together, and that the atomic number tells you the number of protons. Assume for these examples that all of the isotopes are neutral and we're not dealing with any ions. Okay, hopefully you had a chance to pause the video and try it. Here's the answers so you can check your work. Hope this was helpful. Have a great day.